Hello all, welcome to this webinar. This is the last one in a series of 3 webinars on microfluidics. My name is Maaike Prange and I'm your host today. Erik Linnaerts will start his webinar on microfluidic droplet generation in a minute. Erik is Technical Product Manager at Micronit. During the webinar you can ask questions through the chat. The selection of your questions will be answered live at the end of the webinar. All questions, however, will be answered and sent to all attendees by email. We will anonymize the questions first. The webinar will take about 60 minutes, including a Q&A of about 10 minutes. Now let's switch over to Erik and enjoy the webinar Let's Make Droplets.
Hello everyone, my name is Erik and today we will be speaking about microfluidic droplet generators. So you might not know anything about microfluidic droplet generators. That's okay, I've got you covered. We'll introduce it. Or you might know a bit more, or even already have a setup in your lab, but you're not an expert yet. So with this webinar, I hope to introduce the topic better, and we'll do that in a broad way. So I prepared some slides, and let's go there. Okay, so let's start by introducing who's actually speaking here. Let's start by introducing the company Micronit. We were founded in 1999, and that's actually quite a long time ago in the field of microfluidics, which is not that old. We're located in the Netherlands and in Germany, and we've served well over 1,000 customers. We're now with more than 100 people here, and we have some ISO certified manufacturing facilities. So I've been working at Micronit for about 5 years now, and in this time I've worked with many customers that were interested in droplet generators. Now I also noticed that there were quite some recurring questions. People wanted to get more clarity on what they need, and many of those questions I'll try to answer today. Probably not very specifically, but helping you, like giving you the steps to further your research, to know how to take the next step and to learn what you need to learn. So, specifically, what we will be talking about today is an introduction to, or are these 4 chapters, you could say. We'll start by introducing microfluidics shortly and droplet generators, what is so special about them. Then we will talk about which droplet generator type do you need. So once you know what droplet generators are, then which one should you get? Then once you have one, what should you know before you actually start your experiments, or even once you've started your experiments. And then at the end we'll talk about how Micronit fits in this picture and what we can do for you. So let's start with the introduction to microfluidics and droplet generators. A droplet generator, in this case a black box, is something with microstructures where 2 separate fluids go in and an emulsion comes out. An emulsion is basically droplets of the one fluid in the other fluid. And it could look like this, for example. Fluids flow from the left to the right, and they get squeezed with a second fluid from the top and the bottom. And then the first fluid, which is called the continuous phase, no, it's called the dispersed phase, enters in the continuous phase. The continuous phase because it's continuous, not interrupted. Then, microstructures are of course difficult to make. They're small, they're hard to make, and why would you do this effort to make droplets? What's so special about them? For that we go to one of the most fundamental aspects of microfluidics, or actually fluids first, and that is that you recognize them probably as being often turbulent and chaotic. Hard to predict, different all the time, like in these pictures of waves at the beach. Now, another example of turbulent flow is here coming from the hoses of these firefighters. It's very turbulent. If this picture would have been made 1 second later, it would look slightly different. The fluids would flow in a different way. However, in my small tap in my backyard, I made this picture, and it's actually not so chaotic. And if I would have made the picture a second later, it would be the same. Only when I put my finger in, it gets disturbed and slightly less predictable. Now, this predictability, this simpleness, this laminar flow versus turbulent flow is very important. And this predictable version actually occurs more if you have small structures. And for the people that like theory, we can have a look at Reynolds number, written here. The Reynolds number is the flow speed times the diameter divided by the kinematic viscosity. So it's basically a ratio between inertial forces and viscous forces. Now back to normal, not nerdy talk. So basically, if you have really small dimensions with the needed diameter here, then you often have the non-turbulent, non-chaotic, very predictable flow. And that could be very nice. And it could be nice to create droplets because it's very predictable. Like in this picture, you see droplets from several droplet generators being combined in one channel, and you see that they are all the same size. So basically, using microfluidics, you get laminar flow, which is very controllable, but also repeatable, and that has many applications. One, if you can control the size and make them all the same, this could be an application on its own. For example, if you want to create particles that are all the same size, or an emulsion with which is very specifically as you want it. But it could also be, there are actually many more options with droplet generators. For example, you could put things in these droplets. Then of course you can count which droplets have something, the sample that you're looking for in them, and which don't. So droplet generators could be a way to get some quantitative data from your reactions or fluids. And also using microfluidics, it is possible, because we're controlling droplets in channels the size of droplets, we can control single droplets, again making it easy to get quantitative results instead of just statistically. Okay. Now, we were talking about what's so special about droplet generators. Why would you take the effort to go to micro channels? And so controllability is one. They're all the same size, unlike maybe when you stir the fluid with a kitchen mixer, they would be different sizes like here. But another reason is because it is small. Because it is small, you might not need so much of your sample. You don't need a lot of fluid to do whatever you want to do with it. Another thing is that because it is small, it responds to temperature changes more quickly. That way thermocycling can be done faster. And the last thing is, if you create droplets on their own size, you need less force and less of your energies dissipated as heat, making it a more efficient process. Okay, so that was an introduction to microfluidics and droplet generators. We know we need them because they're we know they're special because you can control them and because they are small. Now that you know this, the next question is, of course, which droplet generator type do you need? Because there are many different ones. Here I show a few, but there are many more. The first one is actually one we saw earlier. Fluids coming from the left to create droplets going to the right, and they get squeezed from the top and the bottom. This is called a focused flow droplet generator. A second example is the T-junction, where fluids, where there's a main channel going horizontally, and then from a vertical channel here, droplets get dripped into the main channel. That was called a T-junction droplet generator. Now a third example is a edge droplet generator. This picture actually comes from a paper. And this method is very different again, where you have the fluid that will be the droplets, that is the dispersed phase. It is forced over a plateau, and then when it falls off, the droplets are created. Now, they all look very different, and there are many varieties even to this. For example, you can change the angle of the T-junction chip between the two channels, and you get slightly different characteristics. Which one do you need? The simple answer, just start using one, and you'll find out what you like and what you don't like, and what's going wrong and what's going right. That's the main advice, and we'll get back to that. But of course, we should start with being smart first. So what can we say about the differences between different types of droplet generators? And for that, we'll focus specifically on two of these, starting with the focused flow droplet generator. So as mentioned, the top and the bottom channel actually squeeze these droplets out. You would say they're sheared. And you can also imagine with this method that if the top and the bottom channel flow faster or with more pressure, that the droplets would be different. There is more force pinching off droplets, and what you'll see is that they become smaller. So that's a characteristic of this droplet generator. Now, if we look at the edge droplet generator, and I added a picture here to demonstrate the method more clearly, you see that droplets falling off this plateau are actually not so much controlled by the second fluid or the continuous phase shearing them, but they're mainly determined by Laplace law, which says that there's a pressure difference, and there's like there's an optimum where droplets prefer to be droplets instead of being on this plateau. So they're not controlled by the continuous phase. Now, that's really interesting. To illustrate this a little bit more, let's have a look at a video of the focused flow, so the first one, where the continuous phase flow is actually changed, and you can see that the droplet size is changing as well. So let's start this video. Here you see the droplets are very small, and you can see that the response of the system is changing by changing flow rates. And now we'll go to a second shot a little bit later in a while. They're already going bigger, and now they're a lot bigger. So this is the same system, the same run, but by changing pressures of your two flows going into the chip, you get a different response. So again, if we look here, you see very tiny droplets, and later in the same experiment, you see very big droplets. Now let's go to the next slide, or back, I should say. So there is a difference, and depending on what you're looking for from your droplet generator, one of them could have your preference looking at this aspect alone. So if you are a researcher and you want to just find out which droplet size fits your experiment best, for example, then and you want flexibility and you want to change it all the time, then having this focused flow where you can change the droplet size in seconds is very nice. This flexibility is very nice. But this flexibility could be a problem if you're in a production environment creating mayonnaise for a food factory. Then everything that has an influence on your result is a bad thing, because you need to be careful and not change it. So you prefer that there is no influence of this continuous phase or the second fluid flow speed. And then you might prefer the edge system. So depending on your wishes, one might be more interesting. Other things that you could think about, which we'll not go through in detail, at least not all of them, is that some types of droplet generators create more droplets per second than other types, so have a higher throughput of droplets. There's also a difference in this dispersity of the sizes between the droplets. As mentioned, if you go to microchannels, the droplets are all the same size, but there's still a difference. Some are more narrowly distributed than others. Also, viscosity of your fluids could have an influence. The resulting droplet size could be different. All of this is a difference. Now let's go to one example, and that is related to this image. Here you see a ultrasound image of a baby in a womb, and ultrasound is basically a pressure wave at a certain frequency, and droplets, you could use a droplet generator to create bubbles, and these bubbles could resonate in the pressure wave of the ultrasound, and they would light up in your image. Now you want these droplets, or bubbles in this case, to be all the same size, because there's only one very specific range where they would resonate with the frequency of your ultrasound imaging system. So you also need a lot of bubbles, because this is something you would use for every ultrasound, for example. So a lot in a production environment, you could say, would make you want to go to an edge system, but because the droplet size is so important, the focused flow droplet generator would be nicer in this case, because they're more monodisperse. The droplets are more equal in size. So this is a way to think about which droplet generator you need. They have different characteristics. Now, what if you want to make nano droplets? Now, microchannels are difficult to make, but nanochannels are, of course, slightly more difficult to make. Also, the smaller your channel is, the smaller the particle that will clog your system and make sure it doesn't work anymore. And also, the smaller your channels are, the harder it is to push fluids through these channels. So many reasons not to want to go to smaller and smaller channels, but you might want to go to smaller droplets. For this, we'll have a look at surface tension to go to one example on how you can make nano droplets without having nano channels. So, interfacial tension, or surface tension, but in this case interfacial tension, is the force per unit length to create new interface. So here you see the arrows, that's the surface tension, basically saying they want this shape to be as rounded as possible, such that there is not a lot of surface area between the two liquids. Now, if you would lower this interfacial tension, it might not be as rounded, it would get more pointy, and that way you can make smaller droplets. In fact, that's what you see in this picture from a paper. This is called tip streaming, and this way, by lowering the surface tension very, very much, you can get this jet, and the jet breaks up into very small droplets. And this is a way to create nano droplets, instead of having just very small channels. Now, there are also other ways to create nano droplets. In some cases, just mixing two fluids could create nanoparticles. This could be done in staggered herringbone mixers, or in the same focused flow setup that we see here on the left. Making the focused flow droplet generator very versatile in that sense. So, nano droplets, you could go to small channels, but it's often smart to think of alternative methods, because going smaller and smaller is not always easy. Still with the question, which droplet generator should you take? There's one more thing to think about, and that is which material should your chip, your droplet generator, be made of, or at least which surface properties should it have. You want to see that the droplets that are created don't stick to the wall of your channel, because then you cannot get them out and they might interrupt with future production of droplets. Here you see a picture of what that's supposed to look like. Now the same chip used with different materials, so basically having not the right surface properties, are shown here. Now you can see that the droplet, right when it's created, is actually sticking to the channel wall, and further in the channel you can see big clusters of what used to be droplets sticking to the wall. So this is not the behavior you're looking for. One example, if you go to single cell analysis, you want the droplets to be an aqueous or water environment, and they would then flow in an oil continuous phase. In that case, regular glass would not work because the droplets would stick to the glass, but other materials or coated glass would work. Okay, so to the next topic, the next chapter of this webinar, let's get started with some experiments, and I'll show you a bit more about that. I'll show you a short video and I'll tell you a little bit of the things about it. I hope seeing the setup actually helps you in understanding better what next steps to take and what things you actually need. So here you see the different components, and altogether they would create a droplet setup. Now the first thing that we see here is a pressure control pump. And I'll say more about that in a second, but at least you need a pump to get the fluids through. The second thing you see here is reservoirs for your two fluids. Of course, they start as separate fluids and they end as an emulsion. They would go through two filters if you don't want your chip to clog, and if you are not sure that your fluids are clean enough. Going to a holder, and then to a waste or outlet reservoir. Now let's look at the chip. If you want to start your research, you should know how to connect your chip, your experiment you run if you want to create droplets. Now what you see here is a lot of things and some useful things. Some things are just there for manufacturing purposes, like these lines here. Some things are just to show our logo or to tell which chip this is. And then there are 5 holes on each side. These holes are all there because they're the standard layout of Micronit, and in this case that one is used. It also fits to the holder, which we'll see in a second. But what is important here is the channels that will be used to create droplets. Now the first one is going through the middle, right there, and this will be the fluid that will become the droplets. Then going around that from one other inlet is the continuous phase, going around that, and the resultant channel going there. So there are 3 holes that should be connected to this chip. Now we take the chip holder and put in our chip to connect it. Or a question I often hear is, why do I need a holder? And that's that's people that have experience with soft material chips. If your material is soft, say chewing gum or PDMS, you can just stick in your chewing and it will be sealed and you can flow fluids through without leakage. But if your chip is very hard or solid, this doesn't work, it will leak. So you need to clamp soft part, which is done in a holder, to seal it, or you can just glue it, but then it's harder to undo that. We just have a look at which holes to connect. So these are the ones that will get the tubing. You need to, or in this case, it's done like this. This is a standard holder of Micronit that is very easy to use. Closing it and the chip will be sealed. But of course, this should be part of the entire system, and also there it can be closed. Now to finish this little movie, basically after this, start the pressure and droplets will be generated. Now, if we look here again, we see the pump, and I want to mention shortly something about the pumps, because this is something we receive questions on quite often. But again, coming from Micronit, I should first tell you that usually we don't offer pumps. You should actually go to different manufacturers. What Micronit offers is the chip, holder, the tubing, maybe filters, and not the rest. So for pumps, you could go to different suppliers, but it is good to know that with these very tiny channels in the chips, the fluid doesn't flow very easily. It takes quite some pressure to get them through with some decent speed. Now, if you would take a syringe pump, they work by slowly moving the piston and slowly building up pressure. You need this pressure to get the response in your droplet generator, and it might take minutes before the chip actually does what you want it to. There are also pressure control pumps, and they respond much quicker because they change the pressure almost instantly. So as an observer, it feels like it's much more instantaneous, and that's something I would recommend, going for a pressure controlled pump. Now, let's continue. First experiments, let's talk about those. What if you already made your setup and you do some first experiments? As I mentioned in the beginning, you could try to be smart about which droplet generator type you need. But this is still a science. There are so many different types of droplet generators. They all behave slightly different, and it's not always easy to know exactly what will happen with your specific parameters and your specific fluids. So just getting started with one teaches you a lot. And yeah, let's look at some examples. This is one we already saw. If you start using your chip and you find out it has the wrong surface properties, then you know exactly what you do need. The good thing is, if you have your chips already, you can coat the surface, so you don't need to throw them away. You can just change your surface properties. Another thing you might learn with your first experiments is either that droplets are generated good, as the upper channel here, or the same channel later in the experiment shown here, with a particle in the channel, and you can see that the droplets formed are much smaller than in the top channel, which is of course not what you want. This is not what you expected, and it's quite random because you didn't choose this particle. Now, if this is a problem you encounter a lot, it might be that you're working with channels that are very small and not something that is really workable for you. So you might want to change your approach, like with the tip streaming or the nanoparticles we talked about earlier. You might want to choose a method where you have bigger channels, but you make droplets in a different way to get them to be smaller. So let's look for more signs for chip improvement with your first experiments. Many chips have a filter in the chip, which is great because then your chip doesn't clog a lot. Now, fluids could go through the channels, for example, with these pointed out with these two arrows, and they go through these narrow pathways shown, for example, here. But if you have particles, say a cell, and it's this big, it might be very hard to get through this filter. So if that's the case, you might learn that the filter gets stuck very quickly and you prefer a chip that does not have a filter. You might find that your droplets are too small with all the parameters as you want them. And this is a nice example because here you see that the droplets are exactly the size of this first part of the after creation of the channel. And if this is the case and you want the droplets to be bigger, you can just repeat the same design but make everything bigger, and probably the droplet size will be as you want it. Now, a final thing you might see, notice is that the dispersity of the sizes between the different droplets might be too much for the approach you take. It will be quite good in basically any method of microfluidic droplet generation, but there's still a big difference between different types. So these were all signs how you can improve your chip once you do your first experiment. Another reason why I would recommend starting your experiments and not researching for too long before you actually start is that it's also a bit of a skill. There are many parameters that influence droplet size. As you can see in the top two channels, changing flow speeds changes droplet size. But there are also sometimes different regimes where the whole behavior changes based on properties. So the same droplet generator in the lowest picture actually shows a jetting regime, where there's not droplets coming off one by one, but there's a jet which then breaks up in droplets. Coming to the final chapter of this webinar. Micronit. Now, at Micronit, we design, develop, and manufacture microfluidics from prototyping to high volume. So basically, if you want to get started and you need some chips, we can offer these. We can make just a few chips to get started, scale with you, help you in design and development, and scale all the way through a commercial application where you need thousands of chips every week. So this is actually quite nice. Basically, if you work with Micronit, there's a one-stop shop, which is something we value. And because we want to make this even more easy for you, we also have many partners. For example, the Flow Alliance, where we collaborate with other partners to offer more capabilities in high-volume polymer production of microfluidics. So this gives you an ecosystem in which a lot is possible, but good to know is that many of our customers are actually in the life science and health fields. So if your field is cell culturing or liquid biopsy or NGS, then we can understand what you're working on. Of course, we're mainly experts in microfluidics, but we work with these markets a lot, so it will be easy to communicate. Then, let's make this a little bit more practical. What if you just really want to get started with something? We have a web store, store.micronit.com, and there you can just buy some chips. You can also buy the holder we saw, actually the little movie we saw earlier. These components can be found on our web store. You can order them there and you can start your research. So the great thing here is that this is probably faster and cheaper than a custom chip designed for you. However, at Micronit, like most of the business we do is actually custom chips, where you tell us what the design should be, or we help you slightly with that, and then we make the chips according to your wishes, which is quite nice if you started with a standard product, but then learn some of the things we mentioned before. For example, the droplets are too big, you don't want filters, those things, then you can change those aspects in a new design and we'll make that for you. Now, we love offering small volumes to begin with, so you can actually start your experiments and scale up and doing your research, finding which droplet generator you really need. But in a manufacturing mindset, one is actually one wafer. You see the glass plate here on the picture, and there are many chips in this one glass plate. So this would be one chip, hoping that you see my mouse. And so one chip can never be made. We always make one full wafer. Unless your chip is the size of a wafer, then you can order typically one chip. But this is also nice to know because it means that the smaller your chip is, the more chips you will get from this ordering one wafer. Of course, you shouldn't just take the smallest chip possible because it also has some disadvantages. Like it should still be able to connect to the holder and should still be able to put on the things that you want to put on. Now, in this manufacturing mindset, there's more to keep in mind if you want to go for this custom chip, and that is that manufacturing is never perfect. There's always some tolerances to the size you have designed. For example, it could be 5% bigger or smaller depending on the product process we use. Also, the shape of what comes out depends on the process we use. Sometimes the channels are a bit rough and opaque, and sometimes they're optically clear and they're very smooth. That's a difference. But another difference is the shape of the channel, and many of these channels you see here are created with a process called wet etching. And I'll show a short animation about that, where you'll see that the channels will be rounded at the edges. So let's look at that. If you start with glass, put on a protective layer, then open this protective layer where you want the channels, put it in an acid bath, and then the channel will grow in all directions. And because it grows in all directions, you get these rounded corners, basically around or under the protective layer. So with this process, this would be the result, and sometimes it's very nice, but sometimes this is not what you're looking for. There are other processes where we can make straight channels, but possibly they're tapered, or they have an angle, or the surface is rough, as mentioned before. So manufacturing is never perfect. This is something to keep in mind if you go for a custom chip. Let's go back to live. I hope with this context, with this content, I should say, I gave you a nice introduction to droplet generators, and I hope that if you're really new to the topic, that you understand how to work with them, what they are, why you would want to use them, and you feel like you know what are the next steps to get to a product that you actually want. And if you were a bit further already, I hope that I gave you something to work with, some next steps to take, and some ways to think about how you should continue your research. Now, that's all I wanted to say, but let's see, maybe there are some questions that I could answer. And we'll have a look at those in a minute. So if you have questions, this would be a great time to type them in the chat. I think they're right in the window where you're looking in this webinar. So I see some questions coming in now. Okay. Longer questions, so I need to read a bit. Yes, so there is a question on creating hydrogel beads, if that is possible with Micronit's products. Yes, that's the answer. I've spoken to people that have used our chips to do this. If I remember correctly, there are some things to keep in mind, because I believe there should not be too much of narrow channels, because then the hydrogels might behave weird. So you might want to go for a chip that does not have a filter, if I remember correctly. But yes, this is possible. And now let's see, there's a second part to this question. If double emulsions are possible. So a double emulsion is where you're making a droplet in a fluid, but then from that you make another droplet. So basically it's a droplet in a droplet. So this is possible with Micronit's products, and we have done this before. But here there's another thing to keep in mind. So we spoke about surface properties, and you don't want your droplet to stick to the side, but you want the other fluid, basically the continuous phase in which these droplets are, to stick to the side. Now, if you make a droplet from that again, the surface properties basically need to change, or you need to use a trick. But this is possible, but usually this goes in collaboration with other parties that can work with these changing surface properties. So this is possible, but let's discuss that personally one-to-one, because there would be more partners involved. Now, more questions. Yes, actually, that's a good point. Double emulsions can also be made simply by putting two droplet generators behind each other. Two holders, and then having a small piece of tubing between them. Would probably be slightly less accurate in the sense that some droplets will have no inner droplet and some might have two, but this is something to try, and it's something that's probably easier and faster to try. Let's see for more questions. For cell sorting applications for high throughput, do we need more pumps for different flow focusing channels in parallel? Yes, so if you want to create more droplets in parallel, this is possible. So this in some droplet generator types, it is possible to put this droplet generating part multiple times on one chip, and the chips are of course very small. And if you have a small holder, which we also have, you can just put many chips together, and that way you can parallelize very quickly. So having 100 droplet generating units is still just a very small device. Also, we actually have a parallel droplet generator on the web store, if that happens to be the type that you're looking for. Now, with regards to pumps for parallel droplet generation, I think in first part it will not really be a problem, especially if you have a pressure controlled pump. You'll just put a bigger vial at the beginning, and that will be okay. I think it's okay, but of course, if you want to have like 200,000 channels in parallel, you might need a pump which has more power. But if you go from 1 channel to 8 channels to 100 channels, I think you can do it with the same pump. But I'm not sure. You should definitely talk to the pump manufacturer, because this is not something we offer ourselves. Let's see for more questions. And there's a question regarding the parallel droplet generator Micronit cells. Should I expect higher dispersity than with the simple unique generator? No. Well, theoretically, yes, of course, because they're different droplet generating parts, and there will always be theoretically a difference. But if they are made on the same chip, they are made in the same process, so they will be almost identical. I think for the purposes of most people using them, it will be the same if you parallelize them. However, of course, if one of the channels gets clogged, if a dust particle gets in and blocks one channel, you might make the smaller droplets we've seen in one of the pictures before in one of these channels. And then, of course, you do get polydispersity, but that's basically a chip breaking down. Let's see if there is more. and I need to read them. Someone asks about the coatings and what is preferable, hydrophobic or hydrophilic. So this depends on what you're making. So if your droplet is from a material like water, an aqueous solution, and it is in a fluid which is an oil, then you want the walls to be hydrophobic. You don't want the walls to like the water, you don't want the walls to like the droplet, because then it will get stuck. However, some people want oil droplets in a water surrounding, and then it's the other way around. You want the hydrophilic surface. Let's see. Okay, I'm not sure if there are more questions. Well, then I think that's it. So we're 10 minutes early. Thank you, and I will give the word back to our host.
Thank you for attending this webinar. We hope you enjoyed it. For new activities, keep an eye out for our newsletter and social media. In the chat, you can find the link to the exit survey, and please fill it in so we can learn from your comments. For now, have a nice day.